Well, good morning. It's 9:34 on Monday, the 7th of November, 2016. It's supposed to be Math Calculus 2, Math 126. Right now, I'm the only one in the room. Hopefully, some more will be coming in. But for now, I guess it's just me. So we'll begin from the current slide. But I did want to make just one announcement, or actually a couple of announcements. Rather strange week that we have here. I mean, not really bad, but just several things happened. Today is pretty normal. As far as I know, hopefully nothing major going on today. However, tomorrow I do have a doctor's appointment at 8 o'clock in the morning. I have to be there for labs at 7. Hopefully I can be through before too late in the day, in the morning, and get back and have time for my 11 o'clock class. I'm planning to do that. However, my 8 o'clock class is done for, so we are meeting tomorrow at 12:30 for my 8 o'clock class. Not everybody can be there, but as many as can will be there. So my office hours tomorrow normally would have been 12:15 to 3:15. Tomorrow it's going to be 1:45 until 3:15 because I'll be making up that class for my because of my doctor's appointment. Okay. The rest of Tuesday is fairly normal. Wednesday. There is something happening on Wednesday. It shouldn't affect this class any, but if you do have a class right before here on the Bessemer campus, in this building, Building A, there will be a fire drill Wednesday morning, 8:30 for the A building. So, if you are here, I don't think either one of you are, or any of the three of you are here at 8 o'clock, but if you are, know that there's going to be a fire drill at 8:30, okay? Hopefully we'll be back in the classroom before 9:30 so we can continue with this class, okay? So that's Wednesday's unusual event. Thursday, we have a faculty meeting at 2:30. So normally my office hours on Thursdays are 12:15 until 3:15. On Thursday, it's got to be 12:15 until 2:15 because I have to leave a little before 2:30 to head over to the faculty meeting that starts at 2:30. Fortunately, it's here on this campus in the Ethel Hall building, but I will have to leave, between 2:15 and 2:25 to be sure I'm there about 2:30 when the meeting starts. Okay, so that's the problem on Thursday. And then comes Friday, okay? Sort of a good news, bad news situation. The bad news is Friday's a holiday. It's Veterans Day. There is no school. Campus is closed. Don't come to campus on Friday. The good news is it doesn't affect this class any. We will, or not, don't meet on Friday, so we won't lose a day there. All right. I think that's all the announcements that you need to know about. There are others. I'll be glad to share those with you if and when you show up. Okay. So let's continue where we left off last time. I've got that we were on page 408, Chapter 7, Techniques of Integration and Strategies for Integration. This is the chapter that doesn't have a, this section is not in the old slide set, in the old book. This is only in the new. We had done the first example there. Let's do the second one. Evaluate this. Let me get my pen activated. Okay. Evaluate this. The integral of dx over the square root of x plus 1. Okay? That's your situation. All right? Now, I wish some of you were here because I want you to tell me what to do next, but since you're not, we can't do that. Here's the first thing I would do on a problem like this. I would rewrite it like this. The integral of, open parentheses, x to the 1/2, that is your square root of x there, plus 1 close parentheses, to the minus 1/2 dx. Okay? Hope you see that is the same integral. Okay? The square root of x in the denominator is x to the 1/2. Okay? And that square root of x plus 1, or x to the 1/2 plus 1, is in your denominator, but it's also under a square root, so that's to the negative 1/2 dx. Okay? Now, their suggestion, which I think is a good one, is let's try substitution. Let's let x to the 1/2, let u equal x to the 1/2, sorry, I'm not writing it in the right, our standard form. Let u equal x to the 1/2. Okay? Then du is equal to 1/2 x to the minus 1/2 dx. Well, that doesn't seem to have gotten what we needed. Okay? That substitution doesn't seem to help. Okay? Unless, of course, we come back up here and do this. Perhaps we'll do the x to the 1/2 plus 1. And then we still got the same du. Okay? And it still doesn't seem to help. Unless, of course, that doesn't seem to work. Okay? Nothing seems to help. Either one of those attempts do. Okay? So what else might we try? I think that the technique to do here then is to rewrite this one as u plus u minus 1. Sorry about that. Okay. U minus 1 is equal to x to the 1/2. Just subtract 1 from both sides of that. Okay? And then du is still going to be 1/2 x to the minus 1/2 dx. Okay? What's in here would then be so let's rewrite our integral that we have here in terms of u then. Your dx from down here would be, this is saying du, let's multiply both sides by 2, and Okay. What I want to do down here is multiply both sides of the equation by 2 and multiply by x to the 1/2. Now that looks bizarre because we're now mixing your x to the 1/2 and the u, okay? Except that in doing this, since x to the 1/2 is u minus 1, that gives you your 2 here, okay? Okay, your 2 is on the outside. Dx is 2 times, and x to the 1/2 is u minus 1, okay? Du, okay? Over u, because that was your u to the 1/2. If u is x to the 1/2 plus 1, then this would be u to the minus 1/2. So, yeah, this is now your new integral in u's. All right, and you can work on this. There's a couple of ways you could have done it, and I sort of wish I'd have done it slightly differently, but this is working out fine too. This would be 2 times the integral. Well, u divided by u to the 1/2 is u to the 1/2 minus u to the minus 1/2 du. Okay? And what that yields is 2 times u to the 3/2 times 2/3 minus u to the 1/2 times 2. Okay? Now, what this gives us is 4/3 u to the 3/2 minus 4 u to the 1/2 plus c. Back that up to see your u was x to the 1/2 plus 1, so this would be 4/3 x to the 1/2 plus 1 to the 3/2 power minus 4 times x to the 1/2 plus 1 plus c. That should be our answer. Let's see how close we got. Okay, there we have it. I'm trying to find it on the page. 4/3, the square root of x, I wrote x to the 1/2. Square root of x plus 1 to the 3/2 power minus 4 times the square root of x plus 1. I wrote x to the 1/2 plus 1 to the 1/2 power plus c. Yeah. Whoops. I left off this. 1/2 power. Sorry about that. That u to the 1/2. Yeah, we got the same answer. Now that was a little tough because your substitution, your first inclination of a substitution, probably wasn't going to quite get you as far as you needed to go, so then try your next one. And that still didn't until you started manipulating the u's and the du's, and then, yeah, sure enough, it does come out. It's a way to substitute, but boy, it was a couple of extra steps that we probably didn't anticipate before. All right, so that was, remember the strategies for integration. First, do any algebraic simplification possible. Cancel terms, do whatever it takes, okay? We looked at several. Number 2, look for potential substitution. We did that on the first 2 examples then. Number 3, consider integration by parts, okay? And you remember, how this goes. And then remember there's also ones that you can have to do it repeated times to bring it down, bring it down, bring it down. But then there's others that if you do it repeated times, you get back to the same form, but even then, that gives you a solution, okay? Now, they do give a couple of examples here, not really examples, but just illustrations. And let's do, just for review purposes, what these are. Okay? The first of these is, what if you had the integral of x to the n, f of x dx? Okay? Now, assuming the f of x can be repeatedly integrated, we can use then integration by parts to keep doing this. Okay? Now, you just have to know what it integrates as. But you see, you want to take the derivative of this term and integrate that term. Hopefully this term isn't getting any more complicated. This one's guaranteed to get simpler the more you integrate. Okay? They say that the f of x can then be anything that doesn't get more complicated. That would be your sine and cosine functions. I was going to say trig. Tangents, no, you don't want that. Okay, but sines and cosines, fine. Exponentials, great. Any power function, a to the x, that's okay. Your hyperbolic sines and cosines, try to avoid those if possible. But even your secant squared and cosecant squared, they simplify as you go. Okay? That was the A. The B part was, what if you had a function like this? The integral of e to the x sine x dx. Well, this one, no matter which one you choose to integrate and differentiate, you're going to sort of basically form a huge circular pattern. You just keep going until you get back at where you started from, and then go from there. So this one, actually you choose whichever you want to be f and what you want to be dv. Let's just let, because it's written this way, u equal e to the x, and dv is equal to sine x dx. I would have done it the other way, but we'll just do it this way just to show it doesn't really matter. Then du is equal to e to the x dx, and v is equal to the antiderivative of sine x dx, which is minus cosine x. Okay? So what we have now is, this will be minus e to the x cosine x. Yeah, that's right. Okay. Minus v du, which would be plus then, because we had a minus, that has a minus, the integral of e to the x cosine x dx. Okay? Do it again, but do it in the same order. Since you let u be e to the x, keep it u to e to the x. Let u equal e to the x, then dv is equal to cosine x dx. Then du is equal to e to the x dx, and v is equal to sine x. Okay? Then this part is this, so your overall, remember you had a minus e to the x cosine x plus vd, or uv, e to the x sine x, minus this time the integral of the bottom here, e to the x sine x dx. But notice this is exactly what we started with. So we're going to add this to both sides of the equation, e to the x sine x dx. Add it over here, integral of e to the x sine x dx. Okay, here that goes out, and here you wind up with two of them, so you have twice the integral of e to the x sine x dx, okay, is equal to, I'm going to rearrange the order, e to the x times sine x minus cosine x, okay, and then divide both sides by 2, and you have what you were looking for. It didn't seem like you ever solved it, but here's what it is. 1/2 e to the x, or e to the x over 2, times sine x minus cosine x. Okay? Now, they write it slightly differently, and remember, don't forget your plus c. Okay. Now, again, integration by parts, doing multiple steps. One like this, you just have to keep doing steps until you get it down to something you can evaluate at the end. The second one of those, you do it until you get a term you've already had. All right, Marcus is here. And let me switch things around. Turn on the projector. Nobody's in here. Glad you're here. Let me say this. I said it on Screencast-O-Matic, but in case since you're here, you might not listen to Screencast-O-Matic. Are you on this campus at 8 o'clock on Monday and Wednesday? Or is this your first class? Okay, good. I was going to say Wednesday morning at 8:30, they're having a fire drill for this building. So if you're here early, like by 8:30, then you're going to have to participate in the fire drill if you're in the building. Okay. Hasn't happened too frequently, has it? No, never mind. No, I didn't say that. Okay, so, but just in case you were, so you would know that. If you were here, where would you be? Most likely the library or somewhere like that? Okay. Well, then you just exit the library, the quickest exit you can get to. And then I think they want everybody going up to the back parking lot. That we wouldn't do that during the fire, but that's what they want us to do now. Actually, what they told us in the email last night when I saw it, or whenever they sent it out, but I saw it last night, they said everybody go to the back doors back there. That's not what you do during a fire drill. You go to the closest exit and get away from the building. I think what they want to do is talk with us afterwards. So I say, let's go out of the building. You won't be in here, but I have a class. Say, go out of the building, the door we're supposed to. Then rather than going to the parking lot down there, we'll go to the one in back. Even though we wouldn't do that during a real fire, because then we'd be walking along next to the building that's on fire, and you don't want to do that. But I think they want to have everybody together so they could review the procedures. Okay. What's that? Do I teach on this campus Tuesday, Thursdays? Oh, yeah. I've got an 8 o'clock class. That's pre-calculus algebra, 9:30 class, differential equations, and then 11 o'clock class, linear algebra. And then also in the afternoon at 3:15, I have physical science too. I don't remember. You'll have to look at the schedule. I made out that schedule. They have us make out the schedule like a year or so ahead of time. That sounds reasonable. Yeah. You what? Okay. Right. With physics. Right. And you don't want to do it that way? Okay. Well, the thing is, I've already got, on Tuesday, Thursday, I've got pre-calculus algebra at 8, pre-calculus trig at 9:30. I don't remember if I have anything at 11, but I know it at in the afternoon I've got physical science. So my day on Tuesday, Thursday is pretty full too. I might have 11 o'clock open, and if I do, we might be able to move that. But, what's that? We possibly could. I'll have to check. Like I said, I think more than a year ago I made out that schedule because they wanted it then, and it makes no sense to make them out that far in advance because things change. I mean, instructors leave, come and go. We've had retirement since then, so we got to go and change the whole schedule. Well, not the whole schedule, but big portions of it, just because not the same people are here anymore. So I'll check and see. But you rather than have to drive twice, just drive Monday, Wednesday, on Tuesday and Thursday. Yeah. Well, I was going to say you come here on Monday, Wednesday, and go there on Tuesday, Thursday, and I'll have to go back and forth. But we'll try it. We'll see what we can do. Okay. Don't want to say no, but I can't say yes right now because I don't know what classes. When I looked at my schedule, in fact, since you asked, let's pause this just a moment here. Okay. Guess we had finished this. We'll discard this for right now. Now, just because you asked, let's pull it up to see. This will be probably trying to find, oh, there it is. I'll just show you what my schedule is looking like now. Since you asked, and you're the only one here, so let's just do this. Since you asked. Well, I thought this would be easy and quick. There it comes. Okay. Well, again, I thought it was going to be easy and quick. It's taking a long time to log in. Okay. Okay, right now, here's what my schedule looks like for spring term. I got a Tuesday, Thursday. I wish this were bigger. I don't know why this is, yuck.
I got a few of them done. I was pushing for time, you know.
Okay.
I'll try to get back here, you know, after a while and finish a few more of them.
Okay.
I got I think 3 or 4 done. I know the project formula. I know number 20. I wrote down something you already walked through it. I know it ain't gonna count, but I went ahead and worked it out.
That's fine.
Just to
Perfect.
show you know.
Good. Excellent. Yeah. Okay. All right. All right. Hopefully we can see enough of this to, we still can't. How do I shrink this? I don't know why it's expanded like this. Do you know where that is? Huh? At the top. Right there? That's tools, right? Ah, there's a zoom, I see. Somebody zoomed this out to 150%. I only want it 100%. There we go. All right. Thank you. Get this back. Well, it's still not where I want it. Yuck. Let me see if I can go back without changing back. Okay. No, it did it. Okay, now I'll do it this time. Okay. Should be 100% now. Ah, now I think we can see it. Okay. All right. Here's what my schedule looks like right now. Obviously, I can't teach all this in portions, but right now my Tuesday, Thursdays, 8 and 9:30 are blocked. 3:45. So yeah, it looks like I do have 11 o'clock open. Monday, Wednesday, have 8, 9:30, 12. That's the one you're in, right? 2 and 3:30. So yeah, it wouldn't be. I wouldn't mind that going to Tuesday, Thursday, because right now I have 1, 2, 3, 4 classes on Tuesday, Thursday, and these are mini terms. I have 1, 2, 3, 4, 5, 6. But those are stacked. No, they're not on Monday, Wednesday. So yeah, it looks like we might be able to do that. But of course, everybody in the class would have to agree to do that. Have you already registered? You have. Okay, one person's already pre-registered for that. The rest of these are pretty small. 3 here, 3 there, 1s and 0s. So anything can happen. But I do have Tuesday, Thursday, 11 o'clock free. What's that? Yeah. So yeah, you can go on and pre-register for it then. And actually, even if we couldn't do 11 o'clock, we could do 12:30 Tuesday, Thursday, because I don't have a class until 3 on Tuesday, Thursday. No, I'm sorry. Here's one at 1:15. That's first thing. Yeah. I don't think I could do 12:30. No, that would be 1:45. So no, it would have to be 11. But I do have 11 o'clock open, so that's a possibility. Okay, that's second mini term. 12:30 is actually first mini term. So yeah, 11 o'clock is open, but now that I look at it, that would be tough because that means I have no lunch hour. I go 8 to 9:15, 9:15 to 9:30 to 10:45. Then if I do that from 11 to 12:15, then this is 12:30 to 5 o'clock. So basically all day with no more than a 15-minute break. So, but there's no guarantee which class is going to make. If it doesn't make, we're okay. But there's a good chance it will. All right, sorry. So there is a chance, but everybody would have to agree to it. Okay? All right, where were we? I think we were here. Okay. Now, where we were before is we're on page, we did example 2 on page 408. That's what I was wrapping up, I think, about the time you came in. And I talked about the A and B number 3 on 408, not example 3, but just thing, integration by parts. We looked at 2 examples of that, or I had. Let's look at the C one at the top of page 409. Here was another integration by part, and I've got to go back and change my ink again. Okay. What if you had the integral of log x dx? Okay. Now, there is no function whose derivative is log x. So how do you take an antiderivative of that? Well, integration by parts is again the solution to this, but this is the one case you don't do something that gets simpler. You do the thing that gets more complicated and do the integration. How would you approach it? U equal log x. Good choice. Du is equal, dv is equal to dx. Right? Okay, then du is equal to (1/x) dx And v would be equal to x. Okay? Now we do our product. Huh? Okay, have you got the new book or the old book? New one. Okay, you're on page 49, right? Okay. This is, what the title of this is Strategies for Integration. This is sort of a review of the other three, bringing them all together, or the other 5 sections we have up till now. We bring them all together and mix them all among themselves. Well, it's nothing really new, it's just a review, strategies. Okay, so this will be the UV, which is x log x, minus v du, which the integral of v du, which is x over x dx. Well, x over x is just 1, right? So what is that? Antiderivative of that. Second, x. So this would be x log x minus x plus c. And that would be a decent one to do that way. Okay? There are others that you do this way, and I don't think we did any like these, but here's one. The integral of inverse tangent of x dx. You do the same way, let u equal inverse tangent, okay? Then du is going to give us something, and now, I don't know if you remember your inverse tangent rules, but if you don't, go to the back. The very last section is integration, but the section right before that is differentiation. And when you see the inverse trigonometric, the derivative of inverse tangent is 1 over 1 plus x squared. Okay? And then if you did a dx equal, let's just do it. Let u equal this, inverse tangent of x, dv is equal to dx, then du is equal to, and if you look at that in the back, you'll see it's 1 over 1 plus x squared, 1 over 1 plus x squared, okay, dx, right? And over here, v is equal to x. Now, if you do your next part, u times v, that would be x times inverse tangent of x minus the integral of v du, and that would be x dx over 1 plus x squared. And how could you do that? Yeah. Second. Yeah, the first one's done. I mean, that's all right. Okay. The second, that integral there, how would you do that? Substitution, exactly. Just do a substitution and got it. We won't do it, but you could. Same type of thing for integral of sine, inverse sine of x dx. You let u equal inverse sine and dv equal dx, then du, and if you still got your hand in the back of the book, inverse sine is 1 over the square root of 1 minus x squared dx, and this would be v is equal to x. Okay? Well, again, this integral would be uv, which would be x over the square root of, no, I'm sorry, I was looking at the wrong one, x times the sine, inverse sine of x, minus the integral of x dx over, the bottom line down here, the square root of 1 minus x squared, which again is a substitution. Okay? Different substitution, but it is a substitution. Okay, so yeah, that's how you do those. So you pick a function in the integrand that you can take a derivative of, then set v dv dx. Most of the time we don't do it that way. Okay. Step 4, I guess is what they call it. Okay. Condition 4, whatever they call this. Consider the form of the integral. Does it fall into one of the categories for which we have a technique? Okay. Is it a trigonometric integral? You know, we did bunches of those, such as sine nx, sine cosine mx. Okay. If so, use those rules. Does the integral contain the square root of x squared plus a squared minus x squared minus a squared, x squared plus a squared? If so, trig substitution work. So, consider those. Let's do example 3. That's one like that. This is the integral of x squared plus 16 to the 3/2 power dx. Okay? That's a 3. It's a pretty ugly 3. Okay. What would be your approach on that? Second? Which kind of substitution? Let u equal the thing in there. Okay, if you did that, then du would be 2x dx, and you don't have a 2x dx. That was not going to work. But this is one of those as a square root, and you have something squared plus something squared. Even if the second something wasn't squared, that's going to be a trig substitution. Okay? Which trig substitution? Do you remember? Okay. Here's how I remember. Think back of your Pythagorean identities. Okay? The first one being sine squared x plus cosine squared x. What's that equal to? 1. Okay? So sine squared x is equal to 1 minus cosine squared x. Or vice versa. Okay? So anything that has a 1 minus something squared, that was going to be a sine substitution. Okay? This isn't. The next one of these was, if you divide everything on both sides by cosine squared, you get tangent squared x plus 1 is equal to secant squared x. Ha ha! That gives you something squared plus something squared. That's the substitution you make. Let x equal tangent x. Tangent theta, not really tangent theta. Okay, so that would be the substitution I would make there. Let me show you the one other one. If you subtract 1 from both sides, then this would be, if you have something like x squared minus 1, or minus a squared, or minus anything with a square root, then let x equal secant theta, because then you're in that form. So those are the 3 trig substitutions. This is going to be your tangent. Okay, so I'm going to erase these because I may need the board. Okay, these sometimes take a while and some space. Okay, so which one did we say we would wind up with? Tangent. Let x equal tangent. Okay, normally it would be tangent theta, except we got something else in here. We got that 16. Okay, 16 is the perfect square of 4. So we're going to let this be 4 tangent theta. Just remember that's what you do. If that had been a 3, x squared plus 3, then this would be the square root of 3 tangent theta. Okay, so whatever is there, take the square root of it, and that goes in front. Okay. Now, when you do these, remember, draw your triangles. Okay? Any one of these trig substitutions. So, as soon as I do this, I'm going to draw my little right triangle over here, right? Let this be my angle theta. And basically, another way to look at this is tangent theta is equal to x over 4, right? Okay, so that would be tangent is opposite x over 4 is adjacent. That gives you your little triangle you're going to play with. Okay, so let's proceed. Okay, if x equals 4 tangent theta, then dx is equal to what? You remember what derivative of tangent is? Ah, yep. Go back to the good old back of the book, to that page right before the integration, that one page of differentiation, and your trigonometric function. If number 15 tells you derivative of tangent is secant squared, so the derivative of 4 tangent would be 4 secant squared, right? So that's going to be 4 secant squared theta d theta. Okay? Sorry. All right. Let's proceed here. If x is 4 tangent theta, x squared is 16 tangent squared theta, right? I'm sorry. I'm getting so I can hardly breathe. I hate to do this in class. Oh, man. I don't know why all of a sudden this morning I had no problems at all. Take that out. Okay. Wow. All right. Now let's take it one more step. X squared plus 16, right, would be 16 tangent squared theta plus 16, right? Because x squared is 16 tangent squared theta. Add 16 to it, you got that. And that would be 16 times tangent squared theta plus 1, right? And what's tangent squared theta plus 1? Secant squared theta. So this would be 16 secant squared theta. Okay? Now, I think we're ready to start plugging in our integral. Here's our integral. The x squared plus 16 is this thing right here, 16 secant squared theta, right? And that's to the 3/2 power, right? Your dx, though, remember, is 4 secant squared theta d theta. Okay? Well, what do we have here? We have 64. I'm going to pull that outside the integral. Secant squared theta to the 3/2 power times secant squared theta d theta. Well, I think we can somewhat simplify that, can't we? You could write this as secant well, the square root of secant squared is secant, so this is secant cubed theta times secant squared theta d theta. Okay? So this is 64 times the integral of secant to the 5th theta d theta. Now, you could do this as a trigonometric problem, or why don't we just go to back to our integration and see what we have for our trigonometric forms. We have one of those, number 48 in the back, secant to the n u du. There it is. It's already done for you. You just plug it in. 1 over n minus 1, which would be for our problem here. Our n is 5. So this would be 64. And the integral of secant to the 5th would be 1 over 5 minus 1 is 4, right? Okay. I've lost it. There it is. Tangent theta. That's tangent u, and that's what we were using. Okay. Secant to the n minus 2, so that would be secant cubed theta, because n was 5. Okay. Plus n minus 2, that's 5 minus 2 is 3, over n minus 1 is 4, the integral of secant to the 5 minus 2, that would be cubed theta d theta. Okay? See it so far? Now, scoot back up to number 42, and there's secant cubed theta right there. In the back of the book. Sorry, got tied up in my own string here. So this will be, and by the way, I think to make it easier here, since you got 4 in your denominator here and here, divide 4 into 64, and that gives you 16. All right? So have that be 16 times tangent theta secant cubed theta plus 3 times the integral, well, we don't need the integral sign anymore because we're going to do that integral. Okay? So I'm going to open me another bracket here. And that secant cubed theta is a 1/2 secant u tangent u, secant theta tangent theta, secant theta tangent theta, okay, minus, plus, I'm sorry, plus 1/2 the log of secant theta plus tangent theta. Yuck. I say one thing and write another one. Okay. Okay. That's the natural log of absolute value secant theta plus tangent theta, and then you have your plus c, I think. Yeah. Okay. And then you close that bracket and close the previous bracket. Sorry about this, I've run out of room. All right. So this will be 16 tangent theta secant cubed theta plus, okay, 3/2, and that 3/2 will be carried throughout here except for the C. I could have left that off. So that would be 3 times 8 is 24. because 2 will go into 16. 8 times 3 is 24. Secant theta, tangent theta, plus, and then the 1/2, we've already dealt with that. So that'll be a 24 again. Goodness gracious, this thing is such a pain. Times the natural log of secant theta plus tangent theta. And then we'll do our plus c there. Yuck. All right, I think that's the answer. Let's see, did they even work it out? Yeah. Whoa. Oh. They got an extra 256 somewhere there that I messed up on. Let's see where that was. X equals 4 tangent theta, that's right. X squared plus 16 would be 64. I must have left off a factor here. Okay, x squared, 16 tangent squared theta. So x squared plus 16 would be 16 tangent squared theta plus 16. Okay, when we raise that, oh, there it is. There's my 64. I pulled that out front. Secant cubed. Nope, they got a 16. I've got a 16. They got a... Oh, that's what I did. Sorry. Square root of 16 is 4. 4 cubed is 64. So this is a 64 inside times 64. That's where you're 256. So this is a 256. That's a 256. Okay, sorry, I messed that up. And then when we... This was a 256. Divide by 4, that gave you 64. Okay. And then divide by 2, I think that gives you a 32 or something. But that's why I'm off a little bit. Okay. But other than that, we got it. That'd be 64 tangent theta secant theta. So this is a 64. This is a 64. Sorry about that. And this then would be a 96, and this would be a 96. Sorry about that. Okay. Other than that, we got it. 64 tangent theta secant cubed theta plus 96 tangent theta secant theta plus 96 log of secant theta plus tangent theta plus c. Yeah. Now, but that gives our answer in thetas. We need to go back to x's. Okay. Yuck. So what I'm going to do, if it's okay, just because I have so little room left, is I'm going to go back and erase everything but my answer. Okay. So I think I can afford to erase all this. Okay. I want my triangle, so don't erase that. I can't get this stuff to erase. There it goes. It sort of goes in fits and starts. Okay. I know I've erased that several times now. We'll get rid of this one because that's messy. Okay. All right, I don't think I need this any longer. I think all I need is that final answer. I'm going to clean that up. So from our trig substitution, this is what we get. Okay, so let me write that down here. 64 tangent theta secant cubed theta plus 96 secant theta tangent theta plus 96 natural log of secant theta plus tangent theta plus c. Okay? I still need to get that back to x. What is tangent theta? Well, we know that. It was there already. Tangent theta is equal to x over 4. Okay? What's our secant theta? Well, secant theta is hypotenuse over adjacent, right? Well, what's our hypotenuse here? That's the square root of x squared plus 16. I'm sorry, plus 16. Because that is, if your adjacent is 4, your opposite is x, then the square root of the sum of those squared is the square root of x squared plus 16. So that would mean the secant of theta would be hypotenuse, the square root of x squared plus 16, divided by 4. Adjacent, right? Okay. So now we can go and plug back in. 64 times x over 4 times, now this is a little messy, but it's doable. You're going to cube the square root of x squared plus 16. Well, that would be x squared plus 16 times the square root of x squared plus 16. Okay? Or, I guess the better way is just leave that as to, so let me go back. I was starting to do that. Let's just leave that to the 3/2 power. Okay? That would be x squared plus 16 to the 3/2 power. That's secant cubed over, and of course that would be over 4 cubed is 64. Okay? Forgot about that, but yeah. Okay? Plus 96 secant theta again is the square root, well, let's write it in exponential form, since their original problem was in that form. That would be x squared plus 16 to the 1/2 power over 4 times tangent theta, which is x over 4, plus 96 times the log, natural log of secant theta is x squared plus 16 to the 1/2 over 4 plus x over 4 plus c. Okay, let's see if we can clean this up a little bit. The 64s look like they go out there, and that gives you an x times x squared plus 16 to the 3/2 power. That's your first term. Plus, and here it looks like you just have 16 into 96. Does that go 6 times? I think it does. Okay. Plus 6 times x squared plus 16 to the 1/2 power. I'm going to put my x in front there. Plus, and then there's nothing you can do with this one, I don't think. So just have this as 96 times the natural log of trying to see if there's any way to simplify this. I don't think so. I think you just leave it like that. X squared plus 16 to the 1/2 power plus x over 4. Now, you might be able to do some monkeying around with the logs there, but I think that pretty much gives it to you. So let's see what they got. Okay. Looks like I still don't have quite the same answer they do. They have 16x. I have x. How did I mess that? Oh. We had 64 tangent theta, and tangent theta was x over 4. Secant cubed theta, which would be x squared plus 16 to the 3/2 power over 64. Oh, I left off the 4 here. I'm missing a factor of 4. I don't see it. It's in here somewhere. I just don't see it. If we had a 16 here, and 4 times 6 is 24 here, and then the 96 we got right. But for some reason, let's make sure that's right. Log of x squared, yeah. But anyway, without taking too much more time, that's how you proceed with that. Trig substitution. And that got a little wacko there. Okay, the C part of this one, this is number 4, is the rational function P over Q for polynomials P and Q? If so, we do partial fractions. So that's the next step we take. If P has a degree at least as large as the degree of Q, we divide P by Q to obtain a polynomial which is easily integrated together with a remainder term, and then that one we use that. So let's, without further ado here, I'm sorry to leave that hanging, but I'm tired of messing with that problem. Let's do example 4. Here's our integral. X squared plus 2x plus 10 over x squared plus x minus 6 dx. How would you proceed to do one like that? They have the same degree, so what did you better do first? Okay, factor if you can, and I know the denominator can factor as x plus 3 times x minus 2, right? But I don't think the numerator factors, because that would have to be a x plus 2 times x plus 5, and that's not going to work. So, second, long division. That's what you got to do. Okay? So let's do the long division first. X squared plus x minus 6 divided into x squared plus 2x plus 10. And what does that give you? X squared into x squared goes 1 time. 1 times x squared plus x minus 6. Subtract, or I like to change signs and add. So if I do that, then that will give me, that goes to 0, this goes to x plus 16. Right? X squared and X squared 1 times. 1 times X squared is X squared, 1 times X is X, 1 times minus 6 is minus 6. Now you could subtract, I like to change signs and add. Make that a minus, that a plus, and that a minus. I mean, that a plus. That a minus, that a minus, and that a plus. Okay? Then add, they go to 0, this goes to X, and that goes to 16. Okay? Now, so our new integral here is now the integral of 1 dx, so that's just integral of dx, plus the integral of x plus 16 over, now I want to go on and factor that denominator. You know, you write this, okay, I'm going to write it up, plus x plus 16 over x squared plus x minus 6. Well, the x squared plus x minus 6, that is x, what do we say? Plus 3 times x minus 2. Didn't we say that? Check and see. X squared minus 2x plus x. Yeah, that works. All right. And that would be a dx then. And guess what? I can integrate that first integral. What's it? X. That's just x. Plus. Now we got to do that part. And how do we do that part? Okay, yeah. It's x squared. I mean, x squared. Goodness gracious. X. Yuck. Okay, that time we got it right. Okay. X plus 16 over x plus 3 times x minus 2 is equal to a over x plus 3 plus b over x minus 2. Partial fractions, right? And if we multiply both sides by that denominator, that goes away, and that goes away, and you have an x minus 2 here. This goes away, and you have an x plus 3 there. And then what's our next step? What's that? What number? X equal 2. So this gives you 18 is equal to, when you plug that in, that goes to 0, and over here you get 5b. Not too bad. Kind of messy, but not too bad. B is equal to 18/5. Yuck. What other number might you choose to plug in? -3. That gives you 13. X equal -3, and that would give you minus 5a, right? Well, then a is equal to -13/5. Okay? Messy, but doable. This will be the integral of, it's actually going to start off with a minus there since I put the a first. So let me do that. That'd be minus 13/5 times the integral of dx over x plus 3, right? Plus 18/5 integral of dx over x minus 2. Okay, I think we can do both of those, right? Don't forget your x. X minus 13/5. What's the antiderivative of dx over x plus 3? Natural log of x plus 3 plus 18/5 times the natural log of x minus 2. Usually we put those in absolute value bars because they can never be negative. Now, if you wanted to, you could raise that thing to the 13/5 and to the 18/5, but I don't see any reason why. This should give our solution. Let's see if we got it. X minus 13/5 log, natural log of x plus 3 plus 18/5 natural log of x minus 2 plus c. Good deal. Now they tell you about the integral table. We've already been back there many times. Final 3 pages of the book consist of a list of forms of many common integrals. Given a particular integral we may want to evaluate, we can get it into the form of one of the integrals in the table. Then we apply the given formula to evaluate, the integral. Here's a few examples. All right, you go with it? Okay. Just give you a little practice with the tables. If this is your integral, the square root of 9 minus 4x squared over x dx. Okay? Now, frankly, if I were doing this, I'm not sure I'd even use the integral table. I guess I might, because it is kind of messy. Yeah, you'd have to, because of that x in the denominator. If you didn't have the x in the denominator, a trig substitution would be just about as easy as using the table. Well, let's go back to the back and see what we got. Okay? Very back of the book, there's integral tables. Okay? And take a look at them. These are forms that have square roots in them, so it's not a basic form, not an exponential log form, not a hyperbolic form, not a trig form, not an inverse trig form, not, here. Now we have forms, it says, involving the square root of a squared minus u squared. That's beginning to look like what we've got, okay? Except we don't quite have a squared minus u squared. It wouldn't be bad if a were equal to 3, then we have 9, the square root of 9. But the u would have to be 2x, because then u squared would be 4x squared. And then you would be in one of these forms, right? All right. So with that in mind, let's see what our answer is. Which form does this look closest to? That looks a lot like number 69. Do you see that? In the back of the book. Okay? Except we have u equal 2x. That means du would be 2 dx. Okay? And x would be u over 2, right? So let's see what our form has us now, okay? And we have a is equal to 3, okay? So this will be the integral of the square root of, that would be our a minus u squared, a squared minus u squared, yeah, over, our x is u over 2, so that put the u down here and a 2 up top. Our dx would be dx equal du over 2. So instead of dx, we put a du here over 2 out here, and the 2's disappear. So now we do have exactly that form. And that form, the answer is, when you integrate that, number 69 says the square root of a squared, that was our 9, minus u squared, that is minus 4x squared, minus a, which is 3, times the log, natural log of absolute value, a, which is 3, plus the square root of our a squared minus u squared, that's 9 minus 4x squared, over u, our u was 2x, plus c. All right. That's what we think the answer is from the back. All right. Let's see how close we came. Square root of 9 minus 4x squared, good. Minus 3 times the log, good. Of 3 plus the square root of 9 minus 4x squared over 2x, absolute value plus c. Yes. So you have to be careful with all your manipulations. Get it in the form that looks closest to what you got. Make sure all your parameters and variables and numbers and everything match up. And then I suggest writing them down like we did. Okay? Get them all there out in front of you, and then every time you need to plug it in exactly from that list. Okay? I think it'll work. Okay? So that was example 5. See if we can do something similar with 6. Okay? Do you have everything you need from 5? Okay. Let's do example 6. Let's evaluate this one. The integral of x sine squared x cosine x dx. Uh-oh. I'm not sure I remember one like this. I know we didn't do any techniques like it. Let's go in the back and see if we find anything in a table that's like that. Now, is that a basic form? It sure doesn't look like it to me. Okay? It's not really a logarithmic or exponential form. So, not those hyperbolics, no. Trigonometric form. That comes the closest, but we need an x in there. And whoa-ho, let's see. I was trying to see if any of these quite look like it. They don't. Okay? Inverse trigonometric forms, not. They don't have square roots of any nature. And they don't have, wow. Seems like I've run out of choices here. Okay? So none of those fit it exactly. Okay? What might we try to do? It doesn't appear in the integral, table of integrals, but does anything like it appear back there? The closest I could get would be your sine squared cosine. Let's see if we can find that anywhere there. Trigonometric forms. Sine squared cosine. Yeah. That's number 57, basically. Okay? Okay? Except that we got the x in there. How do we deal with that? Integration by parts, exactly. Let u equal x. Okay, that's the easy part. And dv equal sine squared x cosine x dx. Okay? Now, I think you're going to find that easy to do without even going to the table. Then, du is equal to dx, right? Now, what would v be then? The antiderivative of that. Well, let's just stop for a minute and treat that as if that was its own integral. What would we do if we had the integral of sine squared x cosine x dx? I don't think you need a table. Let's just take a look. Wouldn't let u equal sine x, then du is equal to cosine x dx, and then what this integral would be the integral of u squared du, wouldn't it? And what would that be? U cubed over 3, right? Okay? So, what was my u? It was sine x, okay? So, if that was my dv, then the v would be sine cubed x over 3. Okay. Before I proceed, I want to make sure this works. Okay? If v is sine cubed 3 over 3, sine cubed x over 3, then 3 times 1/3 would be 1 sine squared x times cosine x. Sure enough, that's it. Okay? Then we can do our integration by parts. So I don't even think the table's necessary here. What does this give us? X sine cubed x over 3 minus the bottom line, which is the integral of, I'm going to put the 1/3 out front, sine cubed x dx. That one now, I think, takes us to the table, don't you? And sine cubed x dx, yeah, there it is, number 38. Okay? So that is going to be x sine cubed x over 3 minus 1/3. And then this one is a minus, so that's going to be a plus. Another 1/3. Times 2 plus sine squared x times cosine x, and then finally a plus c. All right? All right. See if we can write down our answer now. X sine cubed x over 3 plus, I'm going to try to put all the pieces together here. That's 1/9 times 2, that's 2/9. 2/9 cosine x plus 1/9 sine squared x cosine x plus c. I think I counted for every one of them. Let's see what we got there. 1/3 x sine cubed x plus 1/9. Oh, they factor out the 1/9. 2 plus sine squared. Okay. They leave it like it is at the top, just with the 1/9 out in front. Okay, which is fine. X sine cubed x over 3 plus 1/9 times 2 cosine x plus sine squared x cosine x plus c. And then they actually factor out the cosine x. X sine cubed x over 3 plus 1/9. Why they factor this way, I don't know. Times 2 plus sine squared x times cosine x plus c. I would have said 1/9 cosine x, but they write it that way. Doesn't matter how you write it, but it does make a little bit of a difference there. I mean, not to the final answer, just how it looks. All right. Good deal. You have to go? What time is it? 11:05? Okay. I'll continue for 5 more minutes. You can pick up what you miss. Yeah. Because we got 11:10, right? Yeah. Okay. All right. I'll try to get one more done, and that'll be example 7. All right. Glad you could make it today. I hate talking to myself, so I'm glad you were here. We'll evaluate this integral. The integral of x times the square root of x squared minus 4x minus 5 dx. All right. Now, on first glance, you might say, will a substitution work? Let u equal x squared minus 4x minus 5. Then du would be 2x minus 4. Actually, I would give that a shot first, okay? Let u equal x squared minus 4x minus 5. Then du is equal to 2x minus 4 dx, right? Then I might also write that du is equal to 2x dx minus 4 dx. Not sure if I want to do this yet, but I'm going to see. Okay. Now, I don't think this is going to help. This part would not be bad to deal with. That 4 dx, that's not pleasant to deal with. Okay? So that's not going to be particularly helpful. Okay? So what do we try next? Okay? Well, this is one of those square root type thing, but this, if we'll notice, is not a perfect square, but it's not that hard from getting to a perfect square. So let's do a little scratching on the side here. X squared minus 4x minus 5. If I separate out that minus 5, I think you'll see why. I'll do it in just a second. I'm completing a square is what I'm doing. Minus 5. Complete the square here, and that would be take half of minus 4 is minus 2. Square it, that is a plus 4, and then subtract 4, and I got the same thing I did before. Okay? That's exactly the same thing we had before. X squared minus 4x minus 5. Except now this part is a perfect square. This would be x minus 2 squared minus 9. And if that's what's under the square root, then this is looking like one of the forms in the back of the book, remember. That's what we're using now. This is a square root of u squared minus a squared. Okay? So, if you let the u equal x minus 2, a equal 3. We have a form of that nature. Okay? And if u is x minus 2, u plus 2 is equal to x. Okay? I think we're going to need that later too. But then what we have here is an integral of u plus 2, that's your x, times the square root of x minus 2 squared minus 9 Let's back off here. I'm sorry, I got my u's and my x's crossed up. Okay. If you let u equal x minus a, then this would be the square root of u squared minus 9 dx. Okay, that would be it. Okay. Now, that doesn't look particularly pleasing because of u plus 2, but let's break that into the integral of u times the square root of u squared minus 9 du. Okay. I never did said that, did I? Du is equal to dx. Okay. So that would be du plus 2 times the integral of the square root of u squared minus 9 du. Okay? Break that into two pieces. Okay? The first piece there looks like, oh my goodness, it doesn't, does it? The second part's no problem, okay? It's the first part that we have to deal with, okay? So that isn't coming out the way I thought it should, and unfortunately, I think we may be almost out of time, but this is exactly how they proceeded in the book. I had a tricky substitution. Okay. So we are proceeding in the right direction. The trouble is, I think we're out of time. Let me pause just a moment.